Hi, good evening students. We are going to discuss the temperature dependence of resistivity. In the earlier classes, we have defined what is specific resistance of a material. It is otherwise called as resistivity of the material of a conductor. So it is defined as the resistance offered by the material to the flow of electric charges and whose length is equal to 1 meter and area of cross section is equal to 1 meter square. So can you recall the expression for the resistivity of the material? Rho. Rho is called resistivity and that is equal to R into A by L, where area of cross section is A and the length of the wire is denoted by L. Okay. Now we have already stated that if the length of the wire is doubled or the area of cross section is doubled, there will be variations in the resistance of the conductor. But there will be no variations in the resistivity of the material, because the resistivity of the material depends only on the nature of the material. So we have studied so far that rho, the resistivity, is a constant. So what does it mean when I say rho is a constant? It is independent of the changes taking place in its length and area of cross section, that's all. But the rho is constant only if the temperature is constant. Only at constant temperature the specific resistance or the resistivity of the material will be a constant. Suppose if the temperature is either increased or decreased, in both the cases the resistivity of the material will also change. That is very important information. So today we are going to study how the resistivity of any material is going to change with the changes in temperature. Okay. Now for that let us take, okay, let rho suffix T, okay, rho suffix T represent resistivity, okay, resistivity of the material at a temperature T degree Celsius. At some temperature, T degree may be 80 degrees Celsius or 100, some temperature T degree Celsius. Similarly, this rho suffix 0, okay, rho naught. This is the resistivity of the same material, okay, resistivity of the same material at some reference temperature T0 degree Celsius. So initially it is a T degree Celsius and this is at a T0 degree Celsius, okay, and now it is found that, okay, it is found that there is some relationship between these two, that is rho suffix T is equal to rho naught into 1 plus alpha times T minus T naught. So this is the expression relating the specific resistance or the resistivity of a material at two different temperatures. Okay, so you can take that, you can take in this case that is T is greater than T0, for example. Okay, so what is the expression relating these two values of a specific resistance? Rho at a certain higher temperature T is equal to rho naught, okay, which is the specific resistance at a reference temperature normally lesser than T, okay, at a T0 degree Celsius, into 1 plus alpha times T minus T0, where alpha is a constant. Alpha is a constant which depends upon the property of the material of the conductor, and it is called as a temperature coefficient of resistance. Okay, temperature coefficient of resistance. So alpha is a constant for any given material. Okay, now I will open the bracket on the right hand side. Okay, so the same equation I am rewriting, that rho suffix T is equal to, if I will open this square bracket, means the first term will be rho naught into 1 is equal to what? It is rho naught, plus the second term is rho naught into alpha, or I can write alpha into rho naught into what? T minus T naught. I bring this rho naught term to the left hand side. So this is rho T minus rho naught, and this is equal to alpha into rho naught into T minus T naught. Okay. Therefore, what is alpha equal to? From this, I want an expression for alpha. Therefore, okay, alpha alone is equal to this rho t minus rho naught. Rho t minus rho naught. Okay, taken in the numerator, and this is divided by the remaining terms is what? Rho naught into t minus t naught. That is in the denominator. Understood? So this rho t minus rho naught is the difference in the specific resistance. It may be an increase or decrease, some change taking place in the specific resistance. Therefore, I can write alpha is also equal to, instead of rho t minus rho naught, I can write delta rho. So this is equal to what? Delta rho. Changes taking place in the specific resistance. Delta rho must be equal to what? Rho t minus rho naught divided by rho naught. Okay, divided by rho naught into t minus t naught. This t minus t naught also, I can represent in the same pattern, that is into delta t. That is the change taking place in temperature. Okay, it will be more convenient for us. So delta t means what? It is a t minus t naught. So I am rearranging this. Okay, I am rearranging this equation. Or alpha is equal to delta rho divided by delta t whole divided by rho naught. So this is one of the equations for expressing the value of alpha. That is the temperature coefficient of resistance is expressed as a ratio. And in that ratio, numerator is once again a ratio, is it not? Numerator alone is what? Delta rho by delta t. So in words, if you say means what? If you say in words, what is the numerator now? Delta rho means what? The change or increase, let us say, the increase in the resistivity of the material per unit rise in its temperature. Understand? Divided by what? The specific resistance or resistivity at 0 degree Celsius or any reference temperature T naught degree Celsius, which is less than T. Okay. So now we have got a definition for alpha. So what is the temperature coefficient of resistance alpha defined as? Slowly and steadily you have to say the definition. Okay, you join with me now. The temperature coefficient of resistance of a material. Okay, the temperature coefficient of a resistance of a material is equal to, or it is defined as, the ratio of increase in its resistivity per unit rise in temperature. Increase in resistivity per unit rise in temperature. Okay, to the denominator. To whom? To its specific resistance or resistivity at T naught degree Celsius. I will repeat very fast once again. The temperature coefficient of resistance of a material or the temperature coefficient of resistivity of a material. Both are one and the same only. That I am going to explain to you further. Okay. So it is defined as the ratio of the increase in its resistivity per unit rise in temperature to its resistivity at T naught degree Celsius. Okay. And what should be its unit? Let us try to find out. The change in resistivity divided by resistivity, both are similar quantities. So resistivity or specific resistance is having unit of ohm meter, and the denominator also is ohm meter. So they get cancelled. So only the term remaining is what? Temperature is in the denominator. Therefore, its unit is per degree Celsius. Per degree Celsius. SI unit. This is Celsius is not SI unit. So SI unit means what? This is per Kelvin. Okay, per Kelvin. Understand? So commonly used unit means what? Per degree Celsius. But you see this expression. Now. Rho is equal to R into A by L. Is it not? That means what? The specific resistance is directly proportional to what? The resistance R. Therefore, a similar equation if I write in terms of its resistance at different temperatures means what? We can also write what? R at a given temperature is equal to R naught. Okay, R naught at a reference temperature T naught into what? 1 plus alpha into T minus T naught. Because rho is proportional to r, I can write the equation in another form. So we get what? Therefore, alpha is also equal to what? Delta r, okay? Delta r divided by delta t, okay? Whole divided by t naught, okay? That is a whole divided by r naught. So this is the expression for alpha. Once again, you have to remember that the value attained from this equation as well as this equation will be the same. So that is why I said the alpha is also called in two ways. One is a temperature coefficient of resistivity or temperature coefficient of resistance. Because both are proportional to each other, the value of alpha will be the same arriving by this method or this method. And the unit is what? Per degree Celsius. So if you look at this equation, how to define alpha once again? Yes, alpha, the temperature coefficient of resistance, is defined as the ratio of the increase in resistance per unit increase in temperature to its resistance at a temperature T0 degree Celsius. Mostly in numerical problems, this temperature T0 will be given as what? 0 degree Celsius only, okay, in competitive exams and all. So have you all understood now? Have you all understood what is meant by temperature coefficient of resistance? Now, there are different type of materials like solids, okay, metallic conductors, insulators, alloys, semiconductors, superconductors. So all these different materials have different electrical properties. Now, for example, I will take the first case, okay, for metals or metallic conductors, okay. Say for example, copper and silver, okay, copper, silver, like that we can take. For metallic conductors, say copper I will take and silver also I will take. For copper, alpha is found to be equal to 3.8 into 10 power minus 3 per degree Celsius. So degree Celsius power minus 1. And for silver, alpha is found to be equal to 3.9 into 10 to the power of minus 3 Celsius, degree Celsius power minus 1, okay, C power minus 1. So this is already very low value only, okay. This is into 10 to the power of minus 3. And for second one is for alloys. So example I will take the alloys, namely nichrome, okay. Particularly nichrome, if you take, means the value of alpha is equal to 0.4 into 10 power minus 3 per degree Celsius. So comparing to 3.8 and 3.9, 0.4 is very, very low value. So both for metallic conductors as well as alloys, you must remember that the value of alpha is positive only. Both are positive. So both alpha value is positive. That is here also for metallic conductors also it is positive. For alloys also it is positive. But what is the difference? For alloys, though it is positive, it is very low than the pure metallic conductors. Then another example I will tell you. Manganese is an alloy. Manganese, okay, manganese. Then constantan. So these alloys particularly, still they have very low value of alpha. That is why they are used to make standard resistances, okay. They are used to make what is standard resistances. So used to make, okay, standard resistances. Why they are used to make standard resistances? Because their resistance and resistivity will not change much with increase or decrease in the temperature, okay. So standard resistances. Then the third point, okay, the third point is for semiconductors whose conductivity and resistivity lies in between that of insulators and conductors. So semiconductors, for example, diode, transistor and all, okay. So germanium and silicon we can take. So for silicon, example I will take silicon. For silicon, alpha is equal to minus 75 into 10 to the power of minus 3, okay, per degree Celsius. Minus 75. So this is negative. But for these metallic conductors and alloys, we have seen that alpha is positive. But for semiconductors, it is what? Negative. That means their resistivity is decreasing with the increase in the temperature. Understand? So when I say that the alpha is positive for metallic conductors and alloys, means what do you mean? As the temperature increases, the resistance also increases and the resistivity also increases. When I say that semiconductors have a negative temperature coefficient of resistance, means what? Their resistivity and resistance decreases with temperature. And along with the semiconductors, you can also take insulators. Okay, for insulators also, what is going to happen if you increase the temperature? Their resistance and resistivity also will decrease with increase in temperature. And in particular, the semiconductor, okay, the semiconductor material, okay, if its value is alpha, means then it is said to have negative temperature coefficient of resistivity. So negative temperature coefficient of resistivity. So what do you mean by saying that a material is having negative temperature coefficient of resistivity? That means its resistivity and resistance both decreases with what? Increase in temperature. In which material it happens like that? Both in insulators and semiconductors. In general, if for any material, if the alpha value is negative, means then such a material is called as a thermistor. So we are introducing a new term. So what is the material which is having a negative temperature coefficient of resistance, means that is called as a thermistor. So thermistor is any material for which alpha value is negative, whose temperature coefficient of resistance is negative. That means its resistivity decreases with increase in temperature. Okay, students, now the same we are going to represent in the form of a graph now. Be ready for that, okay? Now let us discuss the temperature dependence of resistivity in terms of graphs. Now look at the first graph. The temperature is taken along the x-axis and it is expressed in units of Kelvin. The specific resistance or resistivity of the material is taken along the y-axis. As the temperature is increased from a lower value T0 Kelvin, the resistivity continuously increases. That is why we say that the pure metals have a positive temperature coefficient of resistance. So alpha is equal to positive. Understand? Alpha is positive for metals. Then the second graph, you see that it is drawn for alloys. For example, I have taken nichrome. And for nichrome, it is a straight line. Okay. If you take a slope for the first graph and the second graph, means the slope of the second graph will be little lesser than that of the first graph. The slope will be lesser. Okay. This shows that they have a weak dependence of temperature. The alloys have a weak dependence on temperature. Okay, so they also have a positive alpha only, but positive value will be very low comparing to that of the pure metallic conductors. We have just now explained by giving the values also. You must have understood. Okay, so the third graph is that for semiconductors, for example, I have taken silicon, and in this case, as the temperature is continuously increased, the resistivity is a down slope. That means it is continuously decreasing. Now, what is the reason exclusively for metallic conductors and semiconductors? We have to explain why they have a positive temperature of coefficient for metals and a negative temperature coefficient for semiconductors. The reason, okay, we are going to explain the reason. For that, you remember the microscopic form of Ohm's law, okay, from Ohm's law. That is, from microscopic form of Ohm's law, we have studied that J vector is equal to sigma times E vector, where sigma means what? Sigma is called as what? The conductivity. Can you remember? We have studied earlier or not? So the conductivity sigma, okay, this is equal to what? N E square tau divided by M. Understand? So this is what M. means what? M means what? The mass of the electron. And E means what? The charge of the electron. And N stands for what? The number of electrons per unit volume. Is it not? It is also called as electron density or the number density. And tau is called the average relaxation time. So, if you take the reciprocal of conductivity, what do you call? That is only called as what? Resistivity. So, the resistivity of the material is denoted with the symbol rho, and this is equal to what? 1 by sigma. 1 by sigma. Therefore, it is what? M divided by N E square tau. So, this equation for resistivity only is very important for us here. So now we are going to explain why the resistivity increases with the rise in temperature in the case of a metal. Now you look at the equation once again. Specific resistance or resistivity rho is given by what? M divided by N E square tau. Is it not? So shall I say that the resistivity is inversely proportional to the number density of electrons? And shall I also say that rho is inversely proportional to what? Tau, the relaxation time, average relaxation time. But the mass of the electron and the charge of the electron will be what? Constants. So I can write that rho is inversely proportional to what? This number density into tau. So these are the two factors. Okay. Now case 1. Case 1. In metals. Okay. In metals. That is metallic conductors like that of the copper. If temperature increases means, okay, if temperature T increases, when the temperature increases, what will happen to the kinetic energy of the free electrons present inside the metallic conductor? The kinetic energy also will increase. As a result, what will happen? They will undergo very frequent collisions with the positive ions. That means what? The average time between the two collisions will be reduced, will get reduced. But the number of free electrons N remains the same or not? As you increase the temperature, the number of free electrons is not going to increase. Only the collision time, okay, is reduced. Number of collisions will take place, okay, in a very shorter time. Therefore, here in the denominator, N is equal to a constant. Because number of free electrons will remain the same at any temperature, okay, but the speed of collisions, okay, will increase. As a result, the time between two collisions get reduced. So this tau gets what? Decreased. Are you all understanding? I hope you must have understood. As the temperature is increased, the kinetic energy of the free electrons will increase. So the collisions will take place very fast. Rapid collisions with the ions will take place, so that the average relaxation time tau gets reduced. Since tau is in the denominator and since tau is getting reduced, this rho is getting increased. Understand? But what happens to the number of electrons per unit volume? It remains the same. That's good. It remains the same. Therefore, rho increases. Understand? Have you all understood what is the reason for the increase in the resistivity temperature? Okay. I hope you must have understood. Now, case 2. Okay. Case 2 for the semiconductors. Okay. For semiconductors. In the case of semiconductors, what is going to happen? As, okay, that is the temperature is increased. If temperature T is increased, inside the semiconductors, the atoms are forming covalent bonds. Understand? So, covalent bonds between the atoms, okay, between the atoms will break. Between the atoms will break. Okay. All the semiconductors are having a crystalline structure. They have a crystal structure. Every atom is surrounded by 4 covalent bonds with the neighboring atoms. So, when the temperature increases, the bonds will become weak. The covalent bonds will break. So, the covalent bonds between the atoms will break. This releases more carriers. So, this releases electrons. This releases what? Additional electrons. Understand? So additional electrons means what? Number n. Therefore what happens? N increases. N increases enormously. Understand? As the temperature increases, more and more covalent bonds between the atoms will break. This releases more and more free electrons which take place in the conduction process. As a result, the number of electrons per unit volume N increases. So what happens if N in the denominator increases means naturally rho has to decrease. And here also what the average time tau between the collisions will decrease. See, this tau will like this here also tau decreases, but it is ineffective. It is ineffective. Why it is ineffective? When you compare the number of increases taking place in the number of free electrons, this value is not going to change much. Understand? It is not going to affect much. So due to the increase in the number of electrons, what happens? Therefore, rho decreases. Therefore, rho decreases. Understand? So these are the reasons for why the metallic conductors, why the metallic conductors have a positive value of alpha. Why the resistivity increases with the temperature. Understand? And the reason for semiconductors having a negative temperature coefficient of resistance. Have you all understood? Okay, let us meet in the next lecture with a new topic. Bye.